So I'm going to do it with my mass, about 68 kilograms. So we're going to go big G, 667, 10 to the negative 11. By the way, you guys know the shortcut on your calculators for big or small numbers? The double E. So 6.67. So, you know, in the olden days, maybe you did times 10 caret negative 11. Okay? But on your calculator, this little button right here, okay, the little double E thing. So you should definitely be utilizing this second comma if you have this type of calculator, the little double E, and then that'll save you a lot of time, and especially when we start doing a lot of these, sometimes you'll make mathematical mistakes. So that'll pop up a little E, and you just go negative 11 like that. Okay, mass of U, so this would be whatever mass you had. For me, 68. Mass of the calculator, now don't forget to convert. So this is going to be 0.3 kilograms. Okay, the distance between us, center to center, 50 centimeters. Again, you must convert to meters. Don't forget to convert. That should be 0.5 meters. And then don't forget the square. So there's a lot of ways for people to make mistakes. This mistake a lot of people make, the conversions, and then the square. That's another big mistake. Okay, so let me do it. I guess I can do it on here, can't I? So 6.67, so you do your little E thing to the negative 11 times 68 times 0.3 divided by 0.5 squared. Okay, 5.44, 10 to the negative 9. Now all of you will get slightly different answers, right? But your exponent should be about the same. 544, 10 to the, something like 10 to the negative 9, hopefully. Good? So anyways, that's the force of gravity. So what do you notice about this number? It's a small number. Yeah, it's a really, really small number. And again, this is why, okay, the calculators don't go flying towards me, right? They don't go attaching towards me. Because it's a small, very, very small force. And the force of gravity with the Earth is going to be larger. The force of friction between the table and the calculator is going to be larger also. However, let's say we were in outer space, away from any forces, away from any friction. What would happen to my calculator? Let's say here's me floating, here's my calculator. What should happen to it? It should start moving towards me. And could we calculate its acceleration? How could we find its acceleration? Okay, F equals ma. So let's just do it just for fun. F equals ma. Let's find out the acceleration of the calculator. Yeah.
So just curious then, like, okay, so if you're like on the International Space Station, why are they afraid of like floating away, and if they should be naturally floating together?
That's a great question. So let's calculate the acceleration and see what kind of number we're getting with the acceleration. So we're going to get 5.44 times 10 to the negative 9 times m of the calculator, which was 0.3 times a. So I'll use my number. If you want to use yours, that's fine. But notice what's true about this acceleration. It's a small number. Yeah, so 1.8 meters per second squared times 10 to the negative 3, 10 to the negative 8 meters per second squared. Okay, so why are they afraid of floating away? Okay, because, well, this would be, okay, that's my acceleration. If you start moving away, let's say this already has, let's say you throw this calculator this way, right? Yeah, there's a force of attraction to it, but it's going to get farther and farther and farther. And as it moves farther and farther away, what should happen to the force of attraction? It should actually get weaker and weaker and weaker. So maybe we want to figure out how long the calculator is going to take before it reaches me. Could we do that? How could we figure that out? Well, we know the acceleration, right? What's the initial velocity? 0. What else do we need to know? One more thing. The distance. Do we know that? Yep. So can we figure that out? Let's just do it. It's a good review, right? Our tests, our finals coming up. So we got 0.5 equals 0 plus 1/2 1.8 times 10 to the negative 8 t squared. I have my calculator. $74.53. Depending on whether you're using my values or not. So it's about 2 hours, right? It'll take me 2 hours, take the calculator 2 hours.
To only go like that much.
Okay, now actually this number is not quite right for 2 reasons.
Shouldn't it accelerate as it gets closer?
Say that again, say that louder.
Start going faster as it gets closer. Like accelerate, shouldn't it accelerate?
Good. So as the calculator moves, so this was the acceleration at this location, right? 1.8 times 10 to the negative 8. As the calculator gets closer, what happens to its acceleration? It increases. Yeah, it's not a constant 1.8 because the force of gravity between you and the calculator actually goes up as it gets closer, which means it will accelerate more. And so you could not simply do this kinematics equation like this. You'd have to do calculus, you'd have to do some derivatives, integrals. So, you know, we're not going to do that here. I'll let you and your calculus teacher maybe figure that out if you wish. There's a second reason as well, though, why the time would be less. Say it out louder. Yeah, so not only is the calculator moving in, what are you doing? You're attracted as well, right? So the calculator's coming in, you're attracted to the calculator, and there you go. Who's attracted with more force? You? Are you attracted with more force to the calculator, or is the calculator more attracted to you? The forces are equal. Yeah, the forces are equal and opposite. So remember, you're attracted to the calculator is attracted to you with equal and opposite force. Look at the equation. Does it matter if I go m1, m2, or m2, m1? No, the force is going to be the same. Now what will be different? The acceleration will be different.